In the previous videos, we explored about the cdev init and cdev add. We actually registered our character device using cdev, and the cdev structure is initialized with a file operation variable. The file operation variable what we created is not yet initialized, so we'll initialize that later when we define our driver's file operation methods, and that's what we are going to explore now. Character driver file operation methods. In this character driver, we will give support to handle the below user level system calls like open, close, read, write, and lseek. So in the previous video, we created a variable of this struct type, isn't it? Struct file operations. This structure you can find in include linux fs.h. This structure is collection of various function pointers, and all these are possible file operation methods for a regular file or for a device file. In this course, we will be using lseek, read, write, open, and release. So you need to implement lseek, read, write, open, release methods in your driver, and after that you have to initialize these member elements by using the struct file operation variable what you defined in your driver file. Let's move forward. First, let's explore the open method. Let's say you have loaded your PCD driver. PCD stands for pseudo character device driver. And let's say your driver has created a device file /dev/pcd. Let's say the user process uses the open system call to open this device file. When open system call is used on this device file, so what happens? The system call is transferred to the kernel. The kernel will process that system call. Now that happens in the VFS, that is virtual file system. From user level, the control is first passed to the kernel's VFS subsystem. And from the VFS subsystem, the control is passed to the appropriate driver's open method. This is an open method. Let's call it as PCD open. This is an open method for the open system call, which is invoked on this device file. So when the VFS receives an open request on a device file or on a regular file, what VFS does is it opens a file by creating a new file object and linking it to the corresponding inode object. I'll talk more on inode object and file object a little later, but for a time being, you just have to remember this. So the open system call execution control is first passed to the VFS, and the VFS finds the appropriate driver and it calls the open method of the driver. When it calls the open method, it passes two arguments. The first argument is pointer of inode associated with file name, the device file name. And the second argument what it passes is a pointer of file object. Let's explore more about struct inode and struct file. During file operation of a regular file or a device file, there are various VFS data structures involved. The important data structures involved are struct inode, struct cdev, struct file operations, and struct file. You may be familiar with this, right? Struct cdev, which represent a character device, and we register this struct cdev using cdev add. While registering the cdev, we initialize the cdev's file operation with our driver's file operation methods. Basically, cdev points to this. cdev has a field which holds the pointer to this file operation variable, what we created in the driver file. Apart from these two are another two important data structures which are involved during file access, whether it could be a normal file or a device file. Let's explore about this inode object and this file object. Unix makes a clear distinction between the contents of a file and the information about a file. So an inode is a VFS data structure. The data structure is struct inode that holds general information about a file. If you want to know exactly what are the general information about a file, you should explore the member elements of the inode. So whereas VFS file data structure, that is struct file, tracks interaction on an opened file by the user processes. The struct file data structure is used to track interaction on an opened file, whereas struct inode holds some general information about a file like file name, the inode number, and other details. Inode contains all the information needed by the file system to handle a file. Each file has its own inode object, which the file system uses to identify the file. Each inode object is associated with an inode number, which uniquely identifies the file within the file system. Basically, the VFS identifies a file using an inode number, so not using its file name. It doesn't matter whether you use the same file today or you may rename the file tomorrow. Doesn't matter what happens to the file, but unless it is deleted, the VFS always identifies a file using its inode number. The inode object is created and stored in memory as and when a new file gets created. A file could be a regular file or a device file. That means whenever you create a file, an inode object is created. That means object of type struct inode, and it will be placed in the memory. What is file object? Whenever a file is opened, a file object is created in the kernel space. There will be one file object for every open of a regular or device file. A file object is of type struct file. This is a kernel space data structure, just like inode, but for every open of a device file or a regular file, a file object will be created. That means if you open the same file, let's say 10 times, then there will be 10 file objects will be created in the memory. There will be one file object for every open of a regular or device file. So the file object stores information about the interaction between an open file and a user process. This information exists only in kernel memory during the period when a process has the file open. The contents of file object is not written back to disk, unlike inode. File object's contents will not be written back to the disk, remember that. It will get created whenever you open a file, and VFS may modify various member elements of this file object, but none of those changes will be written back to the disk. Whenever you close a file, so the file object will be destroyed by the VFS. But that is not the case with inode. So each file has its own inode object, which will be there in memory, and if there is any change in the inode's member elements, then that will be written back to the disk. So now let's understand, what happens when you create a device file. This will give some clear picture how our system call execution gets connected to our driver methods. Let's say a device file is created either manually or by using UDEV. I will explain the UDEV device file creation later. Whenever a device file is created, so this function gets called init underscore special underscore inode. This is called by the VFS, and this function you can find in fs/inode.c. Here you see the virtual file system passes the device number, right? So the device number of the newly created device file. Look at this code here. And I said whenever you create a device file, inode object will be created. That inode object's address will be passed here. And the VFS also sends what kind of device file it is, whether it's a character device file or a block device file or a FIFO, something like that. It mentions the mode in this argument. This code decodes the mode. Here it is checking for is char. So is it a character device file, something like that. If true, look at this code. The inode's I_RDEV, that's a device number. So where I stands for inode actually, is initialized to the RDEV. That is the device number of the newly created device file, which is passed here. That means now inode is formed and inode's device number field is initialized with the device number of the newly created device file. And after that, inode has one more field called I_f_. So this field, I_f is a pointer variable of type struct file operations. And this is initialized to default character file operations. All these things happen when you create a device file. What is this default character file ops? This is defined in fs/char_dev.c. This is actually dummy default file operations. So the only thing this does is contain the open that then fills in the correct operations depending on the special file. Basically, this is a dummy file operations which has only open and lseek method. This is a dummy open method, char_dev_open. So we'll see later how this is being used in the VFS. That's what happens. These two main activities happen when you create a device file. VFS calls this function and it initializes newly created inode's object with default character file operations, and it initializes the device number field of the newly created inode object with the device number of the newly created device file. And the inode object will be there in the memory. And later when you call the open system call, so all these activities happen. So in the previous slide you understood that whenever a device file is created, an inode object is created in the memory, and inode object's device number is initialized, and inode object's file operation field is also initialized with dummy default file operation methods. Inode object is there in the memory now. Whenever the user level program executes open system call on a device file, these are the kernel level functions get involved in processing the open system call. It first executes a do sysopen kernel function in the kernel space, and that calls do file pointer open function. This is a place where a file object will be created. Remember what I said in the previous slide, for every open, a file object will be created in the kernel space. That file object creation happens in this kernel function, do file pointer open, because the file object controls an open file. And after that, do underscore file pointer underscore open calls do underscore dentry underscore open. In this function, what happens is the default dummy file operations will be called. What is default dummy file operation? This one, char_dev open. So char_dev underscore open will be called. And from char_dev underscore open, your driver's open method will be called. These are the activities involved in an open system call processing in the kernel space. If you want more details regarding this, you can refer to Understanding Linux Kernel 3rd edition, page number 524. This is a very nice book, so you should refer to understand internals of Linux kernel. So basically what happens is whenever file object is created in do a file pointer open, the default FOPs will be called in the do dentry open. So what's the default FOPS? That is this one. This one will get called. And from here, your driver's open method will get called. Let's check the source code of do_dentry open. Here it is. So this function you can find in fs/open.c, and here it is. This is a newly created file object pointer. And take a look here what happens. The struct file also has file operation variable, a pointer variable. That gets initialized here. That means inode's file operation field is copied into file object's file operation field. And after that, you can see that at this point, open method of dummy default file operation is called. That means this function gets called. Char_dev_open gets called. Here, let's explore this function. It's a very important function. Let's explore this. So I would like to directly take you to the complete source code of this function. Here it is. You can go to fs/char_dev.c. Here just search for char_dev open. Right, here it is. Here you see what happens. First, the cdev field is checked. inode cdev field. Initially, it will be null actually, right? Because this function initializes I_rdev and I_fof. It doesn't initialize I_cdev. Initially, this field will be null. That is checked here. If it is null, then these things will get executed. Look at this line. So there is a lookup. Lookup for cdev. That is the cdev what you added using the cdev add. There's a lookup for cdev. Take a look here. How does that lookup works? That lookup works by using the device number. So while you used cdev add function, you added the cdev to the VFS by using the device number. And now here, by using that device number, the cdev will be retrieved. That is, the cdev object what you added is retrieved. Basically, this line doesn't extract the cdev object directly. So instead, it actually extracts or looks up for another kernel object called kobj. By using this object here, it extracts the cdev object. Basically, it uses container of function. I will talk more on container of little later because we use a container of in our driver source code as well. The container of macro gives you pointer to parent object. cdev is the parent of kobj actually. By using the child object, the container of extracts pointer of the parent object. So the parent object here is cdev. It's like that. So we'll understand more on that later. And it initializes this local variable. This is a cdev pointer. And look at this line. That newly extracted cdev object is initialized to inode's I_cdev field. That's how inode's cdev field gets initialized. That means this newly extracted cdev object is nothing but what you added using cdev add. After that, you can see that here. Take a look into this code now. So there is a FOPS variable which is of type struct file operations. FOF pointer gets initialized by using cdev's. This is cdev. P is cdev. Here it is. cdev's file operations. This is nothing but your driver's file operation pointer. Who initialized this? This is initialized by cdev init. Remember that? That is now copied into this local variable, and there is a replace of file operations. So the file pointer had the dummy default file operation, right? That is now replaced by actual file operations of your driver. And after that, here you go. file object, file operation, open. Now this calls your driver's open method. That's how the open system call gets connected to your driver open method. Just spend some time with char dev open function so you will understand. If you are confused, now let me summarize. So now there are two parts. One is when device file gets created, and another part is when user process executes the open system call. You have to understand this in two different scenarios. First scenario is when device file gets created. How device file gets created? Either from UDEV or from manually by running some device file creation commands. First, create device file using UDEV, let's say. So when the device file gets created, inode object gets created in memory, and inode's i_rdev field is initialized with device number. And inode object's file operation field is set to dummy default file operations. That is default char_FOS. That's a dummy one. That's it. Inode object is in the memory. And when user process executes open system call, so user invokes open system call on the device file. Remember that whenever open is executed, kernel first creates a file object for that. File object gets created, and inode's file operation gets copied to file object's file operation. That is dummy default file operations of char device file. After that, open function of dummy default file operations gets called. That is char_dev_open. In char_dev_open, inode object's i_cdev field is initialized with cdev, which you added during cdev add. Lookup happens using inode i_rdev field. Sixth point is inode cdev FOPS. This is the real file operations of your driver gets copied to file object's file operation field. And after that, finally, from file object file operation field, the open method gets called. That is the real open method of your driver. So this is a pictorial representation of how the flow goes actually. There will be a in-memory inode object, and in-memory inode object has a pointer field that is i_cdev, and this will be pointing to your cdev object, what you added using cdev add. And this cdev object has file operation field. This file operation field is pointing to your driver's file operation. That file operation field is copied into file object's file operation field. And this is a file object which controls an opened file. From here, the open, read, write, close, all system calls will get connected to your driver's methods. When you use the open system call on the device file, it returns, isn't it? What it returns? It returns the file descriptor. That file descriptor is actually a reference to the opened file object. So reference to this file object is returned as file descriptor. And the subsequent read, write, and close system calls must use this FD as a reference to deal with the assigned file object in the kernel space.